This is our last of the three interpretations of the definite integral that we're going to do in this class. We've already done area and net or total change. If you go on and take Calculus 2, as promised, you'll see many more. This one is called average value. So here's a question. If you wanted to estimate the average temperature during a day, what would you do? Think for a minute, pause the recording, think about what you would do to make that happen. And I hope your answer would be something like this. You would measure the temperature at a bunch of evenly spaced times during the day. So maybe measure it once an hour, so measure it 24 times. So at many evenly spaced times. So you've got all of these different temperatures for the day measured. Maybe you've measured them at 24 different times. What are you going to do with all those values that you've collected? If you want to get the average, you're going to add them together and divide by the number of measurements. So measure the temperature at many evenly spaced times, add these values up, and then divide by the number of measurements. That's how we would probably all think about trying to compute an average temperature. But now that will just be an estimate, right? Because you won't have actually measured the temperature at every moment along the way. Who knows? Maybe between 2 o'clock and 3 o'clock when you measured the temperature, there was some sudden thunderstorm and the temperature dropped a lot, and you missed all of that data because you didn't measure it often enough. So if you wanted to get how could we find the exact average temperature, what would you do to make that happen? Take a second and think about that. Remember that this is a calculus class, and what do we like to do in calculus class? We like to take the limits. So we would let the number of measurements go to infinity. But otherwise, do the same thing. In other words, measure a whole bunch of times. So if n is the number of measurements, measure n times, add them all up, divide by n, and look what happens as n goes to infinity. So that's what we're going to do. So we want to talk about how to find the average value of any function. Function could represent temperature, could represent population, could represent anything at all. So if we want to find the average value, is the name that we give to this, the average value of a generic function, y equals f of x, on any old interval from a to b. You're going to do the same thing that we talked about there. You're going to take your interval, whether it's 24 hours or 5 minutes or 2,000 years, divide it up into n equal size pieces. How wide will each of them be? We've seen this several times now, b minus a over n. So how will we find the average value of this? We're just going to try to formalize what you said over there, what I hope you said. I have such high confidence in you guys. You can tell, I hope. We're going to measure all of these values. So we're going to take f of x1, f of x2, right? These are all the different temperatures that we're measuring during the day until the very end, f of xn. You added up all of those temperatures or all of those populations or whatever it was you were measuring, and then you divided by n. This should look familiar. It might look a little bit more familiar if I wrote it like this. The limit as n goes to infinity, f of x1 plus f of x2 plus f of xn, all times 1 over n at the end. When have we ever done something like this before? F of x1 plus f of x2 all the way up to f of xn. That's a right-hand Riemann sum, right? And when we take the limit as n goes to infinity, that's how we get our definite integral. The only difference is this 1 over n. So let's look over here and remember what it is, how we actually did define the definite integral. It didn't matter whether we used the left or the right-hand sum, so I'm just choosing the right-hand sum here. We took the area of the first rectangle, meaning its height times its width, plus the height of the second rectangle times its width, and so forth. This was our right-hand Riemann sum, and we took the limit as n goes to infinity, and we called that the definite integral. One way that I could rewrite this is instead of multiplying by delta x each time along the way, like if you're actually writing a computer program to do this and you wanted to do it as quickly, as optimally as possible, instead of doing all these unnecessary multiplications as intermediate steps, you would add up all of the numbers, add up all the y values, and then just do one multiplication at the very end. That would make your program run much, much faster. So I can just factor this delta x out. This thing here at the end is delta x. If I factor that delta x out at the end, delta x is b minus a over n. So this is what the definite integral equals. Do you see that's almost exactly what we've got there, but not quite? What's the difference between this definite integral, which we already know how to compute by our beautiful fundamental theorem of calculus, and this new thing that we're trying to compute, the average value of a function? There's one small difference, and the difference is that here we have a b minus a, and here we have a 1. So if I took this thing, which I know how to compute, the definite integral, and I divided it by b minus a, or I multiplied by 1 over b minus a, do you agree that we would get this? If I take this whole thing, multiply it by 1 over b minus a, that will cancel that b minus a on the top, and I'll get a 1 just like I did over there. In other words, this is 1 over b minus a times the integral from a to b of f of x dx. Because if this symbol here, integral from a to b of f of x dx, is this. If I multiply that by 1 over b minus a, it cancels this b minus a, and I have what was on the previous line there. So this is going to be our definition of the average value of a function. If I want to find the average value of any function at all, whether it has some contextual meaning like temperature or population, or is just some function, this is the way that we need to do it. So now that we've got that definition down, and we have an applet, by the way, that will let you can play with it right now if you want. A way to look at this graphically, this is a very analytical way of looking at it. There's a nice graphical way to do it. But instead of me doing it on the board, we're going to let you explore and see if you can discover how the graphical interpretation is. But let's try one example. So the velocity of our hummingbird that we have seen many times this semester, or at least a couple times, is v of t equals t squared meters per second. We'd like to find out its average velocity between time 1 and time 4. So this hummingbird is basically going on some trip, and we want to find out how fast it was going on average. If you yourself go on a trip in the car, for example, how do you find out what your average velocity was? Probably you don't do an integral. Probably you look at the odometer in the car at the start of the trip, and at the end of the trip, you figure out how far you traveled, and then you divide it by the distance, by the time that you were driving. So I think we're going to see that that's really what we're doing here. So according to our definition, the average velocity on the interval from 1 to 4, according to what we just did on the previous board, we're supposed to take 1 over 4 minus 1, the integral from 1 to 4 of t squared dt, which is the same as saying the integral from 1 to 4 of t squared dt over 4 minus 1. But now we can think back to our previous interpretation of the definite integral as a net change. T squared is the bird's velocity. So if I integrate the velocity from 1 to 4, what does that give us? That gives us the change in the bird's position. In other words, this integral is how far the bird moved, and on the bottom is how long in time the bird was moving. So that's exactly what you said you would do, I hope, to compute the average velocity on your own trip. How far you travel divided by the number of minutes that you were traveling. And then the fundamental theorem tells us how to do this. We need to find an antiderivative of t squared. That's t cubed over 3. We're evaluating that from 1 to 4. This is all divided by 4 minus 1. So we've got, this is really a 3 on the bottom, and then we've got another 3 there. So this is like a 1/9 out front. Plug in the top one, 4 cubed minus 1 cubed. So 4 cubed is 64, minus 1 is 63, and 1/9 of that is 7. 7 what? What should be the units here? You expect the units. We're trying to find an average velocity. So the units should be meters per second. Let's see graphically if we can understand why that is. The integral we did was of this function from 1 to 4. And the units up here were meters per second, and the units down here were seconds. So each of my little rectangles in this picture, what is the units on the area of one of those rectangles, the units on that are the vertical units, meters per second, times the horizontal units, seconds, and therefore meters. So this integral is measured in meters, but what are the 4 and the 1 measured in? They're measured in seconds, so we get meters over seconds, which is exactly what we expect. Now, one warning. Almost every semester, somebody decides, you know what, I found a shortcut that's easier than this method. Instead of doing this whole thing with the integral, what am I going to do? I'm just going to take the velocity at the start, so v of 1, and the velocity at the end, v of 4, and add them together. Does this give the same answer? Let's check. V of 1 is 1 squared, that's 1. V of 4 is 4 squared, that's 16 over 2. Is that the same answer? No. So this is not a legal way to do it. And let's see if we can understand why this is. Suppose that you are going on a trip again to visit your grandparents. What is your velocity at the start of the day when you're just getting into the car? Sitting in your driveway, your velocity is 0. What's your velocity when you get to your grandmother's house? 0 again. So if you applied this method, your velocity at the start would be 0, your velocity at the end would be 0, your average velocity, according to this method, would be 0. And yet somehow you do manage to move about the planet and go visit people and go pick up groceries and go do all sorts of things like that. So this ignores every velocity along the way in between, right? So this is completely illegal, doesn't work, don't try it. The beauty of the definite integral, when we go from 1 to 4, is it is really looking at every single value all along the way between 1 and 4, whereas this crazy method is just looking at 1 and 4, and that's why that method does not work. So as I said, we have an applet for you to experiment looking at this graphically, and we have a check your understanding, so you can try this on your own.